Hello everybody, thanks for coming to the 26th International Congress of Mechanical Engineering. My name is Ian Silva and I'm here with my friend Fernanda Barbosa. We are going to present the preliminary sizing method for hybrid electric powertrain propulsion systems of eVTOL aircrafts. We are both from University of Brasilia. Thanks for coming. So, the summary. Number 1. Introduction. Number 2. Power generation system. Number 3. Methodology. Number 4. Results and discussion. Number 5. Conclusions. Introduction. First, we have the whole contextualization of the scenario. We have the UAM market development through the years. We also have the eVTOL aircraft maturation. We have the low specific energy of the batteries used by the aircrafts. We are here to provide hybrid propulsion system for eVTOL aircrafts to improve the performance and range. So we have first the eVTOL technologies. The flying car. After the Great Wars, World War I and World War II, hybrid inventions between the automobile and the airplanes were tested. This started the first VTOL prototypes. The VTOL enhancement. The maneuverability of a helicopter with the range of an airplane in a single aircraft appealed to many sectors, including the military. The evolution of processors. The evolution of 21st century technologies allowed processors to become lighter and smaller, allowing development of drones and consequently eVTOL. The eVTOL technologies are categorized in 5 categories. We have vector thrust, lift plus cruise, wingless or multi-rotor, hover bike or hover device, and electric watercraft. So we have made an aircraft comparison. We made a survey of existing projects and their main features. We have made a comparison relating maximum takeoff weight, range, and payload. For our case, the multi-rotor category was elected, and the vehicle that stands out is the Surefly, that's shown in the image on the left. The power generation system. Here we have a system called pure electric propulsion system, powered exclusively by batteries and is determined by the energy density characteristics and capacity of the energy storage system. We have batteries that are directly connected to electric motors that provides the lift of the aircraft. Here we have a hybrid electric propulsion system. We have a combustion engine connected to an electric generator that feeds the vehicle's batteries. Then these batteries are then used to power the motors responsible for the lift of the aircraft. Here we have the specific energy, and as shown in the graphic on the left, gasoline can have up to 6 times more specific energy than batteries, and also was found that biosustainable fuel can be an optimal choice. Here we have our methodology. We are going to have some preliminary characteristics of the eVTOL vehicle. Category: multi-rotor. Maximum takeoff weight: 1,000 kilograms. Payload: 250 kilograms. Range: minimum of 100 kilometers. Endurance: minimum of 1 hour. And here we have our sizing method. First, we have the determination of hover power required by the aircraft. Then, we are going to have the determination of the required power delivered by the generation system. And then, we are going to find combustion engine consumption parameters that matches with our generation system. And then, we are going to estimate the battery system's mass. And at the end, we are going to have the preliminary endurance. Determining the power of VTOL motors in hoverflight. So we have some input parameters like MTOW, number of rotors, coaxial efficiency, efficiency of electric motors, MTOW over thrust ratio, and G over W efficiency. And the equations can be seen on the right. First, we find a maximum thrust, then a maximum thrust provided by each motor. Then we are going to calculate the thrust required by the rover, and then we are going to have the total power required by the eVTOL motors. Then we are going to determine the minimum power that the hybrid electric propulsion system should generate. And we have the input parameters, the rectifier efficiency and the generator efficiency. And the required power equation can be seen on the right. About the combustion engine consumption parameters, we are going to set the engine characteristics from data obtained on required power. The specific fuel consumption parameter is important to preliminarily determine the vehicle's fuel mass. The power delivered by the combustion engine must be greater than the power required, as we can see on the equation below. So here we have the calculations of the battery mass of the system. We have these input parameters: battery usage time, specific energy, and battery usage capacity. And the equation can be seen on the right. And finally, we have our endurance. As the input parameter, we have the fuel mass compared to the maximum takeoff weight. We have the G/W efficiency and also the specific fuel consumption. And the endurance equation can be seen on the right. Finally, we have our results and discussion. On the left, we can see the input parameters of the simulation. We use the SFC S6, and we have changed the G/W efficiency from 7 to 10. As we can see on the right, the required power changes a lot when we change the efficiency. What also changes a lot? The endurance. We can have almost 1 hour with 7 G/W efficiency, and we can have more than 2 hours if our G/W efficiency is close to 10. Here we can also see another simulation where we have used 9 G/W efficiency. We have changed the SFC from 4 to 7. As you can see on the endurance, we are going from 2.7 hours of endurance to 1.57 hours of endurance when we have a SFC of 7. Over here, we have a comparison of a hybrid electric and a pure electric system. Here we have used the same input parameters and the same G/W efficiency, but as you can see, the battery mass is a lot bigger in the pure electric system than in the hybrid electric system. But in the hybrid electric system, we have the fuel mass. We have the fuel mass that we don't have on the pure electrics. But what is really nice about this simulation is that the hybrid electric can provide almost 110 minutes of endurance, while the pure electric system can have almost 21 minutes of endurance. So the conclusions are: the G/W efficiency is very important for our calculations, and we have also to find more data and more experimental tests to achieve the optimum value for our calculations. A G/W ratio greater than 7.5 guarantees that the vehicle's endurance will be greater than 1 hour preliminarily. And we also have found the minimum combustion engine power of 173.33 kilowatts, or 232.44 horsepower. SFC and specific power. The best combustion engine is the one that can supply enough power and energy to the generator while adding minimum mass to the aircraft. Conclusions. Pure electric versus hybrid. The hybrid electric system presents an increase of 530% of endurance compared to purely electrical systems. And that's it. Thank you, everybody. My name is Jan, my friend is Fernanda. We are from University of Brasilia. Here you can see our emails for contact. Thank you.